I was talking about complexities of sets. In the first part of the talk, actually, we dealt with sets of points. And in the second part, we moved to some kind of upper level, and we were talking about complexities of families of continua. In the talk for today, we are going to deal with equivalence relations and their complexities. And again, in the first part, we will deal with relations between points, say in compact spaces or continua. And in the second part, we deal with relations between continua, mainly actually relations given by a homeomorphism. Okay, so first of all, let me start with a simple relation. So suppose that we have a compact space X, and we define the following equivalence relation E. So E is formally a subset of the Cartesian product X times X in the following way, that a pair XY is in E if and only if the points X and Y belong to the same component of the space X. Okay, and naturally we can ask, what is the complexity of this E? Well, note that E is a subset of this Cartesian product. This is a Polish space, X times X. So we can ask about the complexity. Well, a lot is known about this E. Well, for example, this is a closed set in the product X times X. Moreover, it is an upper semi-continuous decomposition of X, which implies actually that we can consider the quotient space X by E, which is actually a zero-dimensional compact space. Okay, so we start with a compact space, we consider its components, and we shrink all of them to points. What we get is a zero-dimensional compact space, and actually these spaces are well understood. We can apply, for example, the notion of Cantor-Bendixson derivative to understand their structure. And moreover, it is known that these spaces are homeomorphic to a closed subspace of the Cantor set. Okay, maybe I should just recall that zero-dimensional, this just means that it is a space which has a base formed by clopent sets. Okay, so this relation is really simple. Okay. Now let me consider a relation which is formed in a similar way, but here we do not use components, but path components. So here we suppose that X is even a continuum, and we define the following equivalence relation F in such a way that a pair XY is in F if and only if X and Y belong to the same path component of X. And again, we can ask what is the complexity of this F. Well, this is actually much more complicated than the previous one. Note that yesterday we proved that a path component is analytic, but we noted that in general it needs not to be Borel. So of course this applies to the following equivalence relation, and actually here it is the same, that the relation F is in general analytic, but it might be non-Borel. Okay, so it is much more complicated in general than the previous one. And well, it was proved by Becker that there is even a compact space which has uncountably many path components, but not perfectly many. path components? Well, here perfectly many, this just means that there is some contour set in the space such that each point from the contour set belong to a different path component. So this result actually witnesses the difficulty of this equivalence relation F. And well, there is a question whether if we consider continua in the plane, whether this equivalence relation is Borel. Again, this is strongly related to a question that I posed yesterday, because by a result of Becker and Paul, the equivalence relation F is Borel if and only if each equivalence class is Borel. Well, and equivalence class of F, this is just a path component, right? So the previous question is in fact equivalent to this question. Okay, so it's actually very difficult to say something about path components. They are kind of mysterious objects, and this equivalence relation is very complicated. Well, but note that in this example and in the previous one, we just studied the equivalence relations and their complexities without reflecting that these really are equivalence relations, because we were just talking or considering this F, and in the previous slide, this relation E, just as a subset of this product space. And we just consider their, say, Borel complexity, or whether it is analytic or co-analytic set in this product. But we would like to study some finer or softer relations between these complexities. Okay, so I have few notes, kind of philosophical notes, maybe rather. So till now, this complexity was described somehow absolutely, but in what follows, we describe how to compare complexities of equivalence relations in some refined way. And actually, most of the results of the previous talk depend on topology, on the space in which the equivalence relation was located, but from now on, actually, most of the results will just depend on the structure of Borel sets where our equivalence relation lives. Okay, but these are kind of philosophical notes, and maybe what is more important is the following definition. So let me just consider now that X, Y are just sets, just arbitrary sets. And suppose that E and F are equivalence relations on X and Y respectively. And we say that a mapping F going from X to Y is a reduction from E to F if for every 2 points X prime in X, X is E related to X prime, if and only if Fx is F related to Fx prime. Maybe it's good to draw a picture what's going on here. So we have this set X here, set Y here, and we have equivalence relations. Say E, which induces some kind of partition, and some equivalence relation F here. Okay, and we say that a mapping F is a reduction if this condition holds, which actually means that if we consider points in some equivalence class here, then it has to be mapped into some equivalence class in this Y. And if we consider distinct classes here, we have two distinct classes, then these are mapped to distinct classes in this Y. Okay, so, well, since we require here that X, Y are just sets, and we don't have any requirement on this mapping F, it holds actually that we can find a reduction from E to F if and only if the number of E equivalence classes is at most equal to the number of F equivalence classes. So this seems like, okay, this is just set theory. This is not important, not interesting, but now we can consider some structure on these sets X and Y. Okay, so in what follows, we suppose that X and Y are Polish spaces. So let me recall that these are just completely metrizable, separable spaces. And we have E and F equivalence relations on X and Y respectively. And we say that E is Borel reducible to F, and we denote it by this symbol, if there is a Borel measurable reduction from E to F. Okay, so there is some Borel measurable mapping F from X to Y, such that 2 points in X are E-related if and only if the images are F-related. And we say that E is Borel bireducible with F if, and we denote it by this symbol, if E is Borel reducible to F and vice versa. Okay, so maybe from the first point of view, these are strange definitions, but it turns out that they are very useful. And it's very good to have this feeling about this definition, okay, that whenever you have E, which is Borel reducible to F, then it just means that E is somehow simpler than F. And if we have the two equivalence relations are Borel bireducible, well, roughly speaking, this just means that they have the same complexity. Okay, so now in this language, we cannot say what is the complexity, but we can compare complexities. We can say, what does it mean to have the same complexity? And we know what it means that E is simpler or at most as complicated as F. Okay, so now let me consider the component relation on a compact space again. So this E is as on one of the previous slides. And using the previous definition, we can state the following theorem, that actually E is Borel reducible to the equality relation on real numbers, which is denoted by this symbol, the equality relation. Okay, so let me sketch the proof of this result. So, so just for completeness, this equivalence relation, equality equivalence relation on reals, this is just the diagonal, right? It is the set of all pairs where X equals Y. So this is the equality relation on R. And what we want to prove, that this E which of course depends on fixed space X, is Borel reducible to the equality relation. Okay, so what we need to find, some Borel reduction. So we need to find F going from X to R, which is Borel measurable, and it has the property that 2 points X and Y in X lie in the same component of X if and only if the images Fx and Fy are equal, right? Because this just means that it is in the equality equivalence relation. Okay, so how can we find such a Borel measurable mapping? Well, first of all, note that we observed already that if we consider a quotient space X over E, then this one is zero-dimensional. And we denote by Q the corresponding quotient mapping. Okay, and zero-dimensional spaces can be embedded into the Cantor set. So there exists a homeomorphic, an embedding, say H, from this space into the Cantor set. An embedding. And of course, this Cantor set can be considered as a subset of reals. So now it is enough to define F as the composition of this quotient mapping and the embedding H, which is a mapping going from X to a subset of R. And of course, if we have X and Y, which are from the same component, of X, then clearly this quotient mapping collapses them to the same point. So it follows that Fx equals Fy. On the other hand, if we have 2 points from different components, then it follows that the quotient mapping make them still distinct. Qx is not equal to Qy. But since this H is an embedding, it follows that H applied to Qx is distinct from H applied to Qy. All right. So especially Fx is not equal to Fy, which means that X and Y are from the same component of X if and only if Fx equals Fy. So this F is really a reduction. Well, it is Borel measurable because it is even continuous this quotient mapping is continuous and this embedding is continuous as well. Okay, so that's the proof of such a result. Okay, so now let me continue with composants relation. Okay, so now, of course, we need to suppose that X is an indecomposable continuum. And if we define E by the following rule, that xy is E if and only if X and Y belong to the same composant of X, then this E is really an equivalence relation, because we suppose that X is indecomposable, which means that two composants are either equal or disjoint. Well, and in order to describe the complexity with respect to this Borel reducibility, I need to define first two equivalence relations. Well, one of them, usually denoted by E0, this is an equivalence relation which lives on the space of all sequences of zeros and ones. And two sequences are equivalent with respect to E0 if and only if all the coordinates, up to countably many, are equal. Okay, so I say here almost equality of sequences. Well, it is known that actually this equivalence relation E0 is Borel bireducible with the Vitali equivalence relation on reals, which is defined in that way that two real numbers are equivalent if and only if their difference is rational number. Okay, so this is the Vitali equivalence relation, and it has in fact the same complexity as this E0. It is Borel bireducible to that. And the other one is equivalence relation, which is usually denoted by E1. This lives on the countable product of reals. And it is defined in that way that two sequences are E1 equivalent if they are equal on all coordinates up to finitely many, right? So this is by the word, what I mean by the word almost. Well, and now there is a very nice result by Soletsky that the composant equivalence relation E is Borel bireducible either to E0 or to this E1. Okay, so it somehow helps to understand the structure of composants in an indecomposable continuum. And what he proved is that there is kind of a dichotomy. There are just two possibilities for the complexity. Well, actually, his proof is based on two facts. One of them is that the relation E is of type F sigma. Now that yesterday we proved that every composant is of type F sigma, meaning countable union of closed sets. And to prove that this equivalence relation E is of type F sigma, this is just the same idea. It can be proved completely analogously. So this is one ingredient for his proof. And the second one is a deep result from descriptive set theory, which is kind of dichotomy theorem by Kehris, Louvaux, and Rosendahl. And that's why he got these two possibilities here. Well, of course, one may wonder what in the composable continua are related to this E0 and what continua are related to this E1. I can give an example here. Well, so the first one is the bucket handle continuum, whose picture is here. Well, if we consider this continuum as X, then its composant equivalence relation is in fact Borel bireducible to this E0. I can give just a rough idea for the reason. Well, we can, for example, consider this vertical cut of the bucket handle continuum. Of course, the intersection is a Cantor set. Here, actually, we intersect every composant of that continuum. And we can consider the equivalence relation, okay, which points are in the same composant. So for example, all these points are in the same composant. And okay, you can find kind of similarity of this equivalence relation on this Cantor set with this E0. But there is a small trouble because, for example, if you consider this Cantor set here, and this represents the points of 0, and this represents the point 1, or the sequence of zeros, say, and this the sequence of ones, then of course these two are not E0 equivalent, but here they are in the same composant, so they should be equivalent. So we need to be a bit careful, and the Borel reduction is a bit more complicated, but this is just a technicality, okay? But it can be proved that the composant equivalence relation is in fact Borel bireducible here with this E0. Another example is the pseudo-arc, and it is known that its composant equivalence relation is Borel bireducible to this E1. Okay, so it's more complicated in some sense. Okay, so let me now continue to the next slide. Okay, so till now we considered equivalence relations of sets of points in some continua or compacta. Now we will move to an upper level. So now we consider Q, the Hilbert cube, and by KQ I denote the hyperspace of all compact subspaces of Q. And we denote by E with subscript H the equivalence relation, which is defined in that way that two compact sets A and B are equivalent if and only if they are homeomorphic, right? So this EH is naturally called a homeomorphism equivalence relation of compact spaces. All right. And now we can ask, what is the complexity of such an equivalence relation? Well, of course, it seems that it is completely that it is so complicated that it is somehow not possible to talk about it. But okay, there are some formal way how to express the complexity of this EH. And There is a surprising result by Zielinski, who identified the complexity of EH with respect to Borel bireducibility. Well, I'm not able actually here to say what it means formally that he identified the complexity, but there is some kind of complexity degree which is well understood, and he proved that actually this EH is Borel bireducible to this well-known complexity degree, which I'm not able to describe here formally because the description is quite complicated. But what I can say that that there are some other results that, for example, this complexity degree is the same as if we consider isometry equivalence relation on Polish metric spaces. Okay, so in a similar way, as we consider here this EH, we can consider isometry equivalence relation, which is defined on all Polish metric spaces. And it has the same complexity as this EH. So this is a very surprising result. 1 year later, actually Chang and Gao proved that if we restrict this equivalence relation EH just to continua, we get the same complexity. Well, in fact, for proving their result, it is just enough to Borel reduce the whole EH to EH restricted on continua. So their result is not so complicated as this one. Again, 1 year later, Češla proved that if we restrict EH just to Peano continua, it has still the same complexity as this EH. And finally, we proved with Pavel Krupsky that if we restrict this EH to absolute retracts, then it has still the same complexity. Well, I should say that absolute retracts, these are just retracts of the Hilbert cube. So these are very nice spaces, especially from the homotopy point of view. And of course, every absolute retract is a Peano continuum. So this one is the smallest class from all of these. Okay, but it is a very intriguing question. How is it with the case if we restrict this EH to finitely dimensional continua? Whether it has still the same complexity or not. There are few results which are dealing with dimension, but they are somehow not satisfactory. Okay, I will be talking about them in a few minutes. Okay, so now I need to recall some topological classes. So I already talked about absolute retracts. So these are retracts of the Hilbert cube. Yesterday I was talking about dendrites. Well, these can be characterized as being one-dimensional absolute retracts. Okay, so we just consider absolute retracts, but in dimension 1. Are infinite continua. These are continua which have a base with finite boundaries. So for example, this Sierpinski triangle is a nice example of an infinite continuum because, well, for any point, we can find some small triangle as a neighborhood. And of course, its boundary has at most 3 points. So that's why it is ring finite. Okay, ring finite compacta, that's clear. And absolute retracts in R2, these are just absolute retracts embeddable in the plane. So this is an example of an absolute retract in R2. It may be considered as some kind of a thick dendrite. Okay, there are some portions of the plane included in this space. Well, and let me note that a dendrite can be characterized as being ring finite and absolute retract in R2. And a simple note that zero-dimensional space is of course always ring finite, because if you have a zero-dimensional space, it means that we have local base by sets whose boundaries are empty, so especially they are finite. Okay, so I described some classes of spaces whose complexities we will examine, and now I need to describe some kind of complexity degree in the general theory of Borel reductions. To do this, I will consider countable graphs. Okay, so really from combinatorics, countable graph, this is just a pair VE, where V is a countable set, the set of vertices. E is a subset of V times V, and it is symmetric. So these are undirected graphs. So especially these objects are countable structures, or can be realized as countable structure with just one binary relation. And we can consider all the graphs whose underlying set is just this fixed countable set of natural numbers. And if we consider this product space, 0, 1 to n times n, then it can be naturally, its elements are codes for countable graphs. Okay, because if you have 0 on some position nm, then it will be just, it will just mean that there is no edge from n to m. And if you have 1, it will be considered as that you have an edge from n to m. And of course, you can consider this with the natural Polish topology, with the product topology, which is Polish. Well, it is even a compact space because it is a countable product of compact two-element discrete space. Okay, so this X can be considered that it is a space whose points represent countable graphs. And now we can consider isomorphism relation of these countable graphs. We will denote it by EG. Okay, and it is a subset of X times X, where 2 points X and Y are EG related if and only if they code isomorphic graphs. Okay, if the graph X is isomorphic to the graph Y. So in fact, this EG is just the isomorphism relation of countable graphs. Well, in fact, 3 decades ago, Friedman and Stanley proved that isomorphism equivalence relation of most countable structures is Borel bireducible to this EG, but countable graphs are kind of the most simpler ones. Another structure which is also simple and whose isomorphism equivalence relation is of the same complexity are countable linear orders. You can do the same, but instead of countable graphs, you just consider countable linear orders. These can be coded in a similar way, into a Polish space. And isomorphism equivalence relation of these countable orders is borrowed by reducible to this EG. Okay, so this describes kind of a complexity degree, which is sometimes called the complexity of countable structures. Okay, so we described objects and this complexity degrees. So now we can state some results dealing with these things. So we are interested in the homeomorphism equivalence relation. And first of all, on zero-dimensional compacta. So this is a result by Camerlo and Gao. They observed that it is actually bireducible with this EG, this isomorphism of countable graphs. Well, actually, it is not surprising if you know stone duality of zero-dimensional compacta and Boolean algebras, because this stone duality translates the problem of being homeomorphic from zero-dimensional compacta to isomorphism of Boolean algebras. And Boolean algebras obtained from metrizable compacta are actually countable, right? Because we have a countable base here. So this is a natural way how to obtain a countable structure. So using the result of Friedman and Stanley, we actually get one of the reductions here. Okay, another results dealing with homeomorphism equivalence relation, but now on dendrites, was proved by Camerlo, Darci, and Marcone. They proved that it is Borel bireducible with this EG as well, right? So it is quite surprising because dendrites are like topological objects, but actually then they can be encoded into countable structures in such a way that two dendrites are homeomorphic if and only if the corresponding countable structures are isomorphic. Well, if you think about that for a while, it is not so surprising because there are quite natural ways how to encode dendrites by some countable structures and ternary relations. Well, these ternary relations will be like 3 points, x, y, and z are related if and only if this y lies between x and z. And using this ternary relation, you can in fact encode all the information of a dendrite. This is everything you need. But of course, you need somehow to be able to catch the countable subset of a dendrite. This needs some technical details. And well, you need to prove that everything is Borel there. But this is usually a technical work. Okay, with Pavel Krupski, we were considering these two results, and we want to generalize both of them. So we considered ring-finite continua. Of course, every dendrite and every, So we observed that this result for dendrites can be enlarged to ring-finite continua, and it is still bireducible to EG. Instead of ternary relations, we just need to use n-ary relations. Okay, but we considered the class of ring-finite compacta, which is a natural class which contains both zero-dimensional compacta and dendrites. But it was a big surprise for us when we realized that actually this is actually too complex. its complexity is not the same as this EG, but it is strictly more complicated. And for the proof, actually, we again use some deep results from this Borel reducibility theory, which is called turbulence, which was introduced by Hjort like 2 decades ago. Okay. Sorry. With my PhD student, Jan Dudák, we also considered the following classes: absolute retracts in R2. We were able to prove that it is of the complexity EG as well. On the other hand, if we enlarge this class a bit to absolute retracts in R3 or to locally connected continua in R2, then these are actually too complex. They are not Borel bireducible to this EG. And in this result, there is quite a nice idea how we proved it. So let me just write some details for this Borel reduction. Okay, so it is a bit informal. I should write that the homeomorphism equivalence relation on this class is Borel bireducible to the homeomorphism equivalence relation of rim-finite continua. Well, the idea is very simple. We observed that, okay, so we want to find a mapping F which goes from absolute retracts in R2 to the collection of rim-finite continua, such that it is a Borel reduction. And we observe that you can just take some K in R2 and you assign to it its boundary in R2. And we were able to prove that this is really a rim-finite continuum. Moreover, two continua K and L in the plane, which are absolute retracts, are homeomorphic if and only if their boundaries are homeomorphic. Okay, so this was quite a surprise for us that for proving this result, we just use our previous joint result with Pavel Krupski about rim-finite continua, and it works. Okay, so now let me recall that on the beginning of the first lecture, I was talking about the following motivation, whether there exists a compact space such that every continuum is homeomorphic to a component of that space. And I explained why the answer is yes, but we can additionally require that no two components are homeomorphic. And I told you that this is not possible, and now I will explain why it is so. So we can proceed by contradiction. So if such a space X exists, then we can consider the homeomorphism equivalence relation on continua, and it is in fact Borel reducible to the equality equivalence relation, because, well, if you have these components we already proved that the component equivalence relation will give you a reduction to the equality on reals, right? But now, if we denote by E0, I was already talking about this equivalence relation. So this is an equivalence relation on sequences of zeros and ones. It is the almost equality equivalence relation. Then we can prove that E0 is Borel reducible to homeomorphism relation on continua. This is what I will explain on the next slide. Okay. This is like the most important thing here. And by transitivity of this Borel reducibility, we then obtain that E0 is Borel reducibility to equality equivalence relation. Okay, because E0 is Borel reducible to homeomorphism relation, and homeomorphism relation is Borel reducible to equality. So we get this, but this is a contradiction with the fact that E0 is not Borel reducible to the equality. Okay, this is kind of a general, well-known fact in the theory of Borel reductions. So the proof is completed, but we need to explain this star. Okay, that E0 is Borel reducible to homeomorphism equivalence relation on continua. So now I will explain it separately. So here the definition is just rewritten, and I wrote it as a lemma that E0 is Borel reducible to homeomorphism relation on continua. So what we need to do? So we need to find a Borel mapping Borel measurable mapping F going from sequences of zeros and ones to continua. Okay, Borel measurable. Such that if we have two sequences, AN and BN, then they are E0 equivalent if and only if the images which are continua are homeomorphic. So we can construct this F in the following way. So we have just a sequence AN of zeros and ones, and we assign to this F the following continuum. I will describe it by a picture. So it will be kind of a sine 1 over x continuum, but somehow modified. So we consider here this limit segment by technical reasons. It will be a segment 0,3. And okay. And we consider the following step function here. We just start with two, say, hills like that. And then we continue by either this one or by that one, depending on whether A1 is 0 or A1 is 1. So the top of the hill here would be 1 plus A1. And then we consider, say, one hill here of the full height. And then we continue by these two as on the beginning. And again, we put this hill of height 1 plus A2. So either this one or that one. And we continue by adding two hills of the full height. Okay, and we continue in this process to get such a function. So its closure actually is a compact subspace of the plane. It is a continuum. And the claim here is that actually such a function f is in fact a reduction. Well, what we need to check? We need to check that if we have two sequences, an and bn, and they are E0 equivalent, then the images are homeomorphic. But note that being E0 equivalent means that an and bn is equal up to finitely many indices. But of course, if we have corresponding pictures, two corresponding pictures, then if you make just finitely many changes at the beginning, it cannot destroy a homeomorphism, right? The corresponding spaces will be homeomorphic. And one needs to check some technical details that if an and bn are distinct on infinitely many indices, then these two corresponding spaces are not homeomorphic. Okay, I don't have enough time to explain the details, but the main thing is that this E0 equivalence can be somehow encoded into continua. Okay, so the last slide is actually dealing with this thing. If you consider that a spiral, this is just a compactification of 0, 1, whose remainder is the closed interval 0, 1, then there are results of that kind that there is an uncountable collection of pairwise non-homeomorphic spirals. And Piotr Means proved that in fact there is a compact space with uncountably many components where these components are spirals and are pairwise non-homeomorphic. And he asked whether his construction can be enhanced to get a compact space whose components are spirals, but such that every spiral is homeomorphic to a unique component. Okay, so no two spirals, no two components can be homeomorphic. And actually, if you consider the preceding reasoning and what we proved actually in the reduction was using just spirals, you get that the answer to his question is negative. Okay, so that's it, and I have finished my talk.
Thank you very much, Benjamin. Questions you can write in the chat, or maybe you can ask. Are there any questions?
The construction in the spirals could be the same. I mean, we can take different sequence and start doing, I don't know how to say, looking around in different ways, or?
Well, of course, there are different ways how to do that, but well, it's of course easy to check that if the sequences are almost equal, then the corresponding spaces are homeomorphic. But the converse is more difficult. That if you have sequences which are distinct on infinitely many indices, then they are not homeomorphic.
Okay. Yeah.
So this causes some technical problems. But maybe I didn't go to your question correctly.
No, yeah. I mean, the idea is the same as in the same 1/x curve, right? In the spirals.
Yes.
Yeah.
Mm-hmm. Yeah.
Yeah.
Mm-hmm.
Thank.
¿Alguna otra pregunta?
Yes. Have you published these results?
Sorry?
Have you published these results?
Yes. Well, some of the results with Pavel Krupski, they are published, and some of these results by me and Jan Dudák, these are still not published, but you can find them on archive.
Okay.
And actually, most of the results, which were a bit older, like before 2005, I think, these can be found in a survey paper by Marcone.
Okay.
He wrote a longer paper about this topic.
¿Alguna otra pregunta?
So these spirals are like the ELSA continuum?
Yes, it is a continuum.
The ELSA continuum.
Okay. Well, ELSA continuum is this kind of continuum, right? It is a compactification.
Of that.
I'm using this word spiral because we wrote some paper which is dealing with compactifications of this 0, 1, whose remainder is a fixed Peano continuum. Okay, and we use this notion spiral, but of course here, yes, the standard notion is ELSA continuum, right? You are right, yes.
¿Alguna otra pregunta? Well, thank you very much, Benjamin.
Okay, thank you also, and I wish you many success during your workshop.
Thank you very much, Benjamin.
I want to thank you on behalf of the organized committee, because it's like midnight in Prague and you accept this talk. So we really appreciate that. So thank you very much, Benjamin.